Okay, I'm going to go through an example of a triple integral. And of course, this is when everything is graphical regions. We're kind of in the rectangular domain right now, where we're going to use x, y, z. A little later, we'll be using cylindrical and spherical coordinates. So that's just, I'm trying to differentiate these two scenarios. So for example, the problem will be integrate x minus z, that's your f of x, y, z, over the tetrahedron spanned by, there's 4 points in a tetrahedron, right? Like in a triangle, there are 3 points. In a tetrahedron, there are 4 points. So the 4 points are 0, 0, 0, 2, 0, 0, 0, 2, 0, and 0, 0, 2. So you can already tell this is kind of an easy problem because everything is kind of symmetric. And actually this one is anti-symmetric. So whenever you see anti-symmetric plus symmetric, immediately think of 0. If I've mentioned this before, it's because this scenario happens just everywhere all the time, and it's because it's a very quick way to evaluate integrals. See, we're already done. That took 1 minute. Now compare it to how many. We're actually going to do it the honest way, and we'll see what that will also get 0, and it'll take a lot longer. So whenever you can find 0 integrals, that's always a great thing. So let's just do it. In the previous video, I said just think of it as a double integral. Think of as f times volume, and set up the volume integral first. Then add f. So this avoids you having to think about strange triple integral geometry. So for a double integral, we need the height function, right? Because we're always in the setting where the volume will lie above a graph, and so we'll have access to the base. Actually, we need the base, and then we also need the height. So we also need the base, but the base is a little easier. So I think whenever you have stuff like this where it's just given in words or it's incomplete information, it's nice to draw stuff out. So if there's incomplete information, helps to draw it. Actually, it's helpful to draw it anyways. So let's just draw this. So in the xy, I think it helps also for 3D regions. Start with just xy or xz or let's say yz projections, and then somehow combine them. So let's just do like xy. And remember, I'm just going to rewrite the points that we have. 0, 0, 0. Then we have 2 in the first one. We have 2 in the second one. And then finally we have 2 in the last one. So if I just get rid of all of the 0, if I get rid of the last components, then really what we have is like 0, 0. We have 2, 0. And we have 0, 2. And that last one is a repeat of the first. So I'm going to draw these 2 and 2. And now if you connect them with lines, we have this triangle. And by symmetry, everything else looks the same. Others are similar. So for example, if I wanted to do zx, then really it's the same stuff, right? I would delete the middle coordinate. So we can get 2, 2, and our region is this triangle. So now we're going to somehow combine these things. And I'm going to put my z up top. I'm going to put a dashed line for my y to indicate it is going backwards. And I'm going to put a regular line for my x. So I'm going to plot all these points. Here's the 2, here's the 2, and here's the 2, and here's the 0. And you can see we're going to get triangles in each case. So first I'll do the zx, what we did here. And then, I mean, you don't need to use colors, it just helps me. And then I'll do the xy. And so really what we have now is this tetrahedron. And this is our surface that we're working with. Okay, so you can see in this example, we can use z as the graph. So really the second step is, are we in step 2? Yeah, so I think step 1 was just draw it out. And so step 2, I think, is you need to choose which variable to graph over. Which variable is the graph. So let's use z. And we'll say z is now a function of x, y. This will be the upper and lower boundaries. Well, actually, the lower boundary in this case is nice. We can just use z equals 0. So now the upper, this will be the more complicated. And we have to use a little geometry to get it. But we're going to use the fact that it's a plane. So the upper surface is a plane. And because planes are the simplest type of surface we know. So planes are easy. And because they have an equation. Other easy things are circles, spheres, and because all of these things have equations. Right? So this is x plus y squared equals 1. This is x squared plus y squared plus z squared equals 1. So the equation for the plane is n times r minus r0 equals 0, where this thing is the normal vector. This thing is x, y, z. Remember, both of these equations involve x, y, z, so we needed to see that somewhere. And finally, this thing is in the plane. So for example, we could have used, if we go back to our figure, this thing, 2, this is in the plane. This is in the upper boundary. And this point, of course, is 2, 0, 0. So we could, for example, use 2, 0, 0. It does not matter which one. Any of these points would work. That's just an example. So what we need is, so the equation just boils down to finding n. So I think this is the third step. We need to find the normal vector. And so the normal vector, I'm just going to draw a general plane here. If we have any two vectors in the plane, tangent vectors, then you can get the normal vector to the plane. You can get that by taking their cross product. So this is A and this is B. then I claim that n, you can get a normal vector by taking A cross B. So this is the normal, and these are two tangent vectors. Okay, so to get n, all we need is just to plug in two tangent vectors. So how do we get the tangent vectors? So we're going to use the known points. Remember, we had 0, 0, 0, we had 2, 0, 0, we had 0, 2, 0, and we had 0, 0, 2. And our tetrahedron looks sort of like this. Okay, so to get two tangent vectors, what we could do is just subtraction. Subtract the points. Right? Because let's just go back to this graph over here. If we start off with 0, 0, 0 here, and for example, if this is 2, 0, 0, okay, then we can get a tangent vector. Okay, let's call this one 0, 0, 0, 2, 0. And let's call this point 0, 0, 2. These are the 2 points. And then what we can do is we can start off with our third point, and to get the vector A, we subtract. So we subtract off 0, 2, 0 from 2, 0, 0. So in terms of this graph here, we get our vector A by subtracting the red from the blue. So right, because remember, the blue vector, it points to a point in the plane, but it's not a tangent vector. Like if we just to illustrate this situation again, if you just go back to 2D and we have a line, then this point here, the vector that points to a point on the plane, it's not tangent. So this thing is not tangent. In contrast, this vector here, which points between two vectors, this is tangent. So tangent vectors point between planar points, not between the origin and the plane. So you need two planar points. That's just a very long-winded way of saying subtract these two things. Okay, so for our B, we'll do the same thing. We will do the third point, 0, 0, 2. So we're using the Z1 and this is the Y1, and we're going to subtract the same X1. Okay, so we end up with negative 2, 2, 0, and we get negative 2 again, 0, 2. So now the normal vector is the cross product. So the normal vector is the cross product, and this is the determinant, I, j, k, and we had negative 2, 2, 0, and negative 2, 0, 2. So to evaluate the determinant, it's always kind of like a diagonal thing. So, for example, the first term will be I, and then the diagonal across from I. So I times the determinant 2, 0, 0, 2, and then you always do a minus sign when you go to the next term. So minus j times, you delete the j column, So minus 2, minus 2, 0, 2. So in the j case, I would use these columns. And finally, again, we need an extra minus sign. So now you get 2 minus signs as a plus, so k. And then for the k, I would use the xy columns. So -2, -2, 2, 0. And so if you get, this is a 4, this is a 4 with minus sign, but we have another minus sign here. This is a -4, but you have to do the minus sign. Again, remember, for example, this is 2 times 2 minus 0 times 0. Those determinants have minus signs. So this is 4i plus 4j plus 4k, also known as 4, 1, 1, 1. And this is sensible. You can always use a sanity check to see if you got the right answer. Just do an xy projection. So that would be 1, 1. And so if we look at the xy plane and we draw our surface, the normal vector 1, 1 looks like this. And this was 2, this was 2. So again, we see it's perpendicular, so that's good. So we have our normal vector, so now write the equation. So our equation for the plane is the normal vector times all tangent vectors equals 0. Remember, this is any tangent vector. Like I explained before, this is it's the difference of two planar vectors. So the normal vector is 1, 1, 1. Clearly we don't need this 4, right? Because you can just cancel it from the 0 on the right hand side. So now x, y, z, that's r, minus, for example, doesn't matter which one you can, but I'm just going to use 2, 0, 0 equals 0. So now expand, and we get x plus, I'm just going to do the first vector times the second, and then the second vector. So x plus y plus z, and now minus 2 equals 0. So this is our equation for the plane. So now you just solve for z. So z equals 2 minus x plus y. Okay, so I think this is the hard part. So if you're not familiar with some of, I would call this early multivariable calculus, you might want to brush up on some of this, but really the only reason we need this is just to get an equation. Okay, so the upper, remember, just to recall our context, we're looking for a volume, so we need our height and our base. So the upper is, so here's the upper, here's the lower. The upper is now 2 minus x plus y. That's going to be our z as a function of x, y. And then our lower is just z equals 0. Okay? So our height is just 2 minus x plus y. Okay. So our integral will roughly look like the integral over our base times our height. And so all we need now is the base, because we have our 2 minus x plus y. And of course our minus 0. This is the upper, this is the lower. Okay? So now we need our base, and I believe we are on step 5 now. So just find the base. And this is just ordinary double integral. This is just from when you were doing double integrals, this should be familiar. So our base is just set z equal to 0 in the equation you found. That equation you found, it was hard, but it gives you a lot. So x plus y plus z equals 2. If you set z equal to 0, you get x plus y equals 2. So now you need to choose a graph. And so, for example, let's use y. So now you solve for y. So y will be 2 minus x. So our base, if we just draw the base out, this is 2 minus x. And we'll do the dy on the inside, and then we'll do the dx on the outside. And just to recall, to find the x limits, we have our y limits. So you can see from the graph, this is the upper base boundary, or edge. The lower, in this example, will be y equals 0. So to find our x limits, just look at the left edge. And the left edge is x equals 0. And the right edge is x equals 2. Okay? So our x limits, they were 0 to 2. Our y limits, they were from y equals 0 to y equals 2 minus x. And then finally, our z, well, okay, we now have the ability to do a double integral. So now we're on step 6. So write out a double integral for the volume. So for example, we'll get 0 to 2, that's our x. Remember, I put x on the outside and y on the inside. So that's exactly how the integral should be too. So 0 to 2 minus x. And then we had z of xy minus 0. And then we have our dy dx. So I would say this was the most complicated part. So now we just add f. Add f by putting z into an integral. So you don't have to you don't have to do this. This is just an extra thing that will help you that might help you just get a feel for what's going on. But really, you could just skip from here to the integral from 0 to z of xy dz. You don't need to write out a double integral if you don't want to. This is just anything that will help you make less mistakes and I don't know, do it quick. Have a better intuition that it might be worth thinking about. So that's equivalent to this integral, right? So now we just need to replace 1 with f. So we overall end up getting the same exact thing. Everything else is the same. So 0 to 2 minus x, and now we have our z integral from 0 to z. In this case, it's 2 minus x plus y. And then now we add our f. And if you go all the way back, we have x minus z. That's what we want to integrate. So our f is x minus z. And now we put our dA, which is dy dx. So that is our triple integral. Okay? And you can see that there's a pattern, right? This is just the x limits. This is the y limits. And this is the z limits. We really didn't need to think about it as a surface and find its volume. Really, you can find the graph, see what the lower and upper limits are, and then just stick integrals next to each other, and you get the right answer. So I think the final step now is just to evaluate. And this part is pretty routine. So I think the only thing to mention is just make sure you fix x and y in the dz integral. So when you're doing this first one, 2 minus x minus y, x minus z, or x minus z dz, fix x and y. So that is to say, we can actually treat x as a constant here. So when we integrate, this is x times z minus 1/2 z squared, evaluated from 0 to 2 minus x minus y. So obviously the lower limit doesn't do much, just goes to 0. This is 0, so x times 2 minus x minus y. And then we have minus 1/2 2 minus x minus y squared. Okay? So now we end up with a double integral. And that's from 0 to 2, 0 to 2 minus x. This is your x integral, this is your y integral. And we have x times 2 minus x minus y minus 1/2 2 minus x minus y squared. Okay? And so this part, I mean, it's a quadratic, so it is doable. It's kind of tedious. But really, again, what you do is you fix y, or I'm sorry, you fix x, and you integrate in y. And this part, because we know double integrals, I'll leave this to you if you want the practice. Really, this is just basically number crunching at this point. I think the hardest part was the setup. It's always the setup. Okay. I hope this was helpful. Thanks for watching.